Hello, welcome also from my side to SpaceSec 2025. Welcome to our first session, to our first paper session after a very interesting keynote. I don't think there are titles for the sessions, but this is very clearly the testbed and data collection infrastructure session. And very much looking forward to it. Our first speaker is Jedermann from the University of Kaiserslautern. Eric will be speaking on a new network built to collect more data specifically for LEO satellite research. So yeah, stage is yours, Eric.
Thanks for the nice introduction. Yeah, as Martin already said, hello, I'm Eric and I'm talking about LeoCommon, a ground station observatory network for LEO satellite research. And this is joint work from our guys from Kaiserslautern and the Cyber Defense Campus in Switzerland. First of all, let's talk a little bit about the motivation, what I did and why I did that all. Everything started for me with my previous work that was presented last year at Usenix, the record attack, which was basically you're eavesdropping on the downlink, so from the satellite to a user terminal. And if you find traffic of a specific user, you can roughly estimate in which region the user is located. So, and for that, we had to collect a lot of data. And for doing so, I was looking around, okay, how are other people collecting data? And found out that most of the time, it's this simple setup, laptop, SDR, antenna, and go for it. Okay, so this was not the easiest or the best way to go for our case, because we had several remote locations where we wanted to record. We needed a quite high number of recordings. Each recording had a very long duration, up to multiple days sometimes, and we wanted to test different configurations. So going there with a laptop and or putting a laptop everywhere and just calling family and friends every few hours like, hey, can you now start a recording with this configuration or that? Not the best idea. So also, we wanted to do simultaneous recordings. So first going in one location, doing the recording, then going to another location was also no possibility. Therefore, we went for a remote-controlled LEO satellite communication recording. And since it should be a general purpose tool, we also looked at other researchers and to figure out which kind of needs they had, which requirements they had to also fit this in our tool. And this is what we came up in the end. We called it LeoCommon. And it's a tool for a distributed and synchronized recordings. It's possible to record decoded messages, so if you're interested in the content of messages, you can use that. Or if you're more interested in the raw signal measurements, then you can also do raw recordings. We can ensure that the quality of our data is quite high. We are aiming to integrate multiple constellations, so it's not only for one purpose, but you can use it for multiple LEO constellations. And everything is open source and should be at low cost. And this is how one of our setups looks like. Okay, it's basically just an antenna and a green weather-resistant box. So let's have a look into that box and the architecture that we built. In general, our system consists of two parts. One is the LeoCommon server. So it's a command and control server that is basically, running everything. It provides a user interface, a nice website. So one can enter this website or the system to download collected data and also schedule new recording jobs and also put in several parameters like which frequency band you want to record, which type of recording you want to do, things like that. And then we have the ground stations. They are regularly pulling on the server to request, hey, is there a new job to execute, and then also upload the job in the end. When looking in the ground stations, their heart, I would say, is a processing unit, a core, and that's built of 3 components, more or less. The first one is our updater, and this updater is connecting to an update server. That's an additional server that I didn't mention before because it's mainly just for the updates. We used Hawkbit and Rauk for implementing that, so we didn't have to invent everything new. And on top of our updater, we're running 2 operating systems. And the idea why we're doing that is basically, let's assume we're currently working in Linux A, this is booted, and we have scheduled an update. So the updater is downloading the stuff and updating the second operating system that we have on our device. Once the update is finished, it reboots in this just new updated operating system, and then it performs several health checks if the system and everything works. In case everything went fine, it continues to work in this new operating system, but in case something failed, then it is capable of rebooting in the old system, Linux A, that was just running, and thereby we can ensure even if an update fails or we misconfigure something, we still have a completely independent second operating system, and our ground station is not lost due to a false update or something. So looking a little bit into our operating systems, of course, we at some point have to connect our SDR to receive some signals, but there are also some more components inside. First of all, we have our ground station client. This is, I would say, the brain of each ground station. This is the client that does most of the work. This is connecting to the central server, pulling for new jobs. It's executing those jobs and also uploading the data in the end. So this is, really the brain of our system or of each ground station. And for executing the jobs, there are several receiver and decoder functionalities. So have a little bit a look into that. Of course, everything starts with an SDR where we're gonna receive some signals, just doing some filtering for that after that. And then, for example, for this case, when we wanna really decode some messages, so we're interested in the content, of course, first step is to detect if there are some messages, decoding them, demodulating them, and storing them. So it's pretty straightforward, I would say. This is basically the tool Jane GR Iridium is already implementing. So if you're familiar with that, that's a pretty useful tool. For the second possibility, when we want to record some raw data, of course, it's also important to detect if something is sent currently, and then something that's very important, and I think everybody who ever did something with raw recordings can understand this. It's pretty important to filter out only those messages that are interesting for us. Otherwise, the recordings get pretty big very fast. So therefore, this is very important. Really just record those messages that are important for us. Then we're trying to compress them to not waste any storage and bandwidth, and then upload them on the server so a user can finally download them and work something with that. Okay, so talking so much about the general architecture and so on, let's look a little bit deeper into the stuff. First, everything is on GitHub. It's completely open source. So if you're interested in that, you can contact us there. You can access it. I also will show this slide at the end of the presentation, so you have plenty of time looking it up. As I mentioned, we have a server. We are using, in our case, a MongoDB with a fast API on top of that and an Nginx for accessing the whole stuff. And this provides access to the user with a web interface or to our ground stations that we just had a look into. And for setting up our system, we evaluated multiple single board computers. As you remember, I mentioned we want to keep the whole system at low cost. So we tested different devices, And we're also considering new devices that we have not yet tested, like the Intel NUC or some other mini computers, everything at low cost. And for really testing the different devices, we have measured the sample loss at different sample rates for each device. And as you can see, if it goes to higher sample rates, the not so powerful devices are dropping more and more frames. Currently, we're working with Raspberry Pi 4, so you can see that it's roughly working until 7 or 8 megahertz. However, if you want to set up such a system on your own, I would recommend using the new Raspberry Pi 5s. They are super good, just to say that. They're much more powerful, and even 10 megahertz doesn't make them sweat, so good thing. Okay, we are running a sensor network or a ground station network, as I mentioned a few times. Currently, we have 10 sensors distributed in Luxembourg, Germany, and Switzerland. And we have a little bit more than 3,400 hours of recording currently, which is about 80 gigabytes of traffic. Now, when setting up one of those sensors, it's pretty important to have a good view of the sky. So when we're evaluating now different, I would say, coverage maps, so which parts of the sky are visible to us, so from which satellite locations are we able to receive some signals. And in some cases, like this one, we have a pretty bad visibility. As you can see in the upper left corner, there's a building blocking everything, and even the rest of the sky is covered by trees, so there we have quite limited visibility. The second case, it's better, but still not good. We don't have so much trees around, but there is one house or one roof corner that is blocking parts of our signal. And this is one of our best sensors that we have. It's one of those sensors that we have in Switzerland. It has a pretty good all-around view, and this is the ideal case that we're looking forward to. Now, those graphs are kind of the sky that we're seeing, so it's the sky coverage that we have. Another important thing for us was our ground coverage. So when we have a ground terminal, a user terminal that's stationed on the ground, and the satellite is sending signals toward this device, in which cases or for which locations of the ground terminal do we have a chance to eavesdrop on this link? This is something that we also considered in our evaluation and did some simulations and calculations. And for the Iridium system that we are currently mainly working on, this is our coverage map. So if we have one sensor in the middle, we have, it's kind of logic. If the user device is more far away from our sensor, our chances of receiving signals for this device are getting more and more reduced. So combining this map with our current sensor systems that we have gives us a pretty good overview of the area that we're currently covering. And you can see that in the red area we have coverage of, let's say, in average 70% or more of the traffic. You can see that complete Switzerland is already covered with that. That's pretty nice. And even when we go to 50%, which is still the green part, we are covering a big part of Central Europe currently. So when talking about setting up such a system, it's also important to talk about which hardware, which options we're currently supporting. And as I said, I would recommend using Raspberry Pi 4 or better 5. And this is about 60 to 70 euros, depending on the version that you want. At the moment, we're working with HackRF1s. They have a pretty good, I would say, support in the hacker community. So they are about $300. I would recommend using a professional iridium antenna from Tower Glass, since this part of our receiver is outside 24/7. So if you have snow, rainy weather, whatever, this has to withstand these weather problems. So that's the only part I would say, okay, having some professional equipment there is a benefit. Trust me, I tried the different way and it's not gonna work. At least not reliable for multiple months. So when talking about network access, we have also different options. The easiest one is to use the built-in Wi-Fi and LAN connectivity of the Raspberry Pis. In case that's not possible, we are currently supporting an LTE head that costs around 70 euros. Or as an alternative, you can use some USB LTE sticks. Pretty straightforward. You just plug them in and they register as a normal network device, and like Ethernet, they are just directly usable. Then we also have some GPS information, because every sensor should know its own location. Therefore, you can either use the LTE head, it's a multi-purpose head, so it's also able to receive some GPS information. Or, as an alternative, use a simple USB GPS antenna. Also, plug-in works pretty straightforward. We also have included a fallback option in case either GPS is currently not working, or, I don't know, maybe you want to save those 20 euros. Then you can also use a hard-coded location that's somewhere in the config file, so it's pretty easy to access. You just have to manipulate or edit our config file. However, we meant this to be just a fallback option, so using a GPS antenna is definitely the better idea in my opinion. And if you sum up everything, you see that we are ending at roughly 500 euros per ground station, which is quite okay, I think. So when talking about the stuff that we used to receive something, let's talk about the quality of the receivings that we have. And in the beginning, we had quite some problems, to be honest. And the most of those problems were related to the timestamps that in the original GR Iridium code is generating. For the timestamps, they're using something like a starting timestamp that's generated when the program is started, and then they do a relative timestamp, which is composed of the frame counter and the sample rate. Sounds okay in the first moment, but if you remember this table, that at some point we experience some frame loss, and as you can see in the gray numbers, even if we're not at the highest sample rates, it always can happen that some frame loss occurs. Yeah, turns out it's a bad problem to use the frame counter for that. So we wanted to figure out how bad this problem really is. Therefore, we had a look in some of our recordings that we made, because there are these Iridium broadcast messages. They're pretty nice. As you can see on the right side, they have a built-in timestamp. So this timestamp is sent directly by the satellite. And on the left side, you can see the timestamp that is locally generated, so the starting time point plus the relative timestamp. And our idea was, straightforward, simply comparing them and figure out what the time offset is. Turns out, we have some time offset. So these are 24 one-hour recordings of one day that we had. And in the beginning, new timestamp and new file is created, everything works fine. But during this 1 hour, we had increasing, cumulating time offsets up to 70 seconds, which is absolutely not great, I have to say. To circumvent that, we modified the code a little bit to always use directly the timestamp of the machine and not some frame counter stuff thing, whatever. And this works quite good. You can see it's close to 0. So let's zoom in a little bit to see how precise we are in reality. And here you can see that we are roughly in 0.06 seconds, so 60 milliseconds that we're working in. And this is quite okay, I think. So comparing this, our local timestamp, to the satellite timestamp that we just received. Another possibility to figure out how reliable our ground stations are is to simply record traffic on multiple of our devices, on multiple of our ground stations, and then compare the timestamps of messages that both were able to receive. So this is something that we did, and this histogram was a result of this. And you can see that it's also plus minus 60 milliseconds, which is in the same region as the previous graph just showed. So it's pretty stable, I would say. Okay, what else could be important besides the time where we receive something? How about the frequency? So similar approach. We were using multiple stations in parallel, recording traffic, looking at at the messages both of our ground stations were receiving and comparing their frequency offset. And wow, okay, 15, 16 kilohertz offset. It's not nothing. So let's figure out now how big of a problem that really is. So let's have a look into the documentation of Iridium, and you can see that one channel is something between 31 and 32 kilohertz wide. So having an offset of 15, 16 kilohertz is borderline okay-ish. In practice, it turns out it's not a problem for us. However, if you want to have more precise frequency stamp, I call it, there are several options to do that. Therefore, let's have a look at what's the reason for this frequency offset that we have. And its main reason is the built-in oscillator in the HEC-RF1 that is precise up to 20 parts per million. So at 1.6 gigahertz, we are expecting roughly up to 32 kilohertz offset, which is in the range of our really experienced offset that you have just seen. So if you want to improve on that, you can use some temperature-controlled oscillators. There we would expect something like 160 kilohertz offset only, which is much better, much better. If you even want to go more precise than that, you can use some oven or GPS-controlled oscillators. However, they become more expensive. So my humble opinion is using the temperature-controlled ones for 20 euros, absolutely fine, absolutely worth. Okay, so when we're already talking about which options you have to upgrade the whole stuff, let's also talk about the plans that we have for the future to work with that. And the first thing to mention there is that we want to integrate an antenna switcher, because the idea that we have is the following. You still have one SDR connected, and this one SDR is connected to multiple antennas. And yeah, it's a bad idea to always screw and unscrew them manually. So this would be our possibility to do this remote controlled. Therefore, an antenna switcher is the way to go. And we're currently working on integrating Globalstar, which is, depending on if you want to look at the up or down link, sending on 1.6 or 2.4 gigahertz. So there we need for sure different antennas. Another pretty interesting system is ORBCOMM, which is sending at a few hundred megahertz. So again, a third antenna that we would need. And let's also talk about the big kid on the block, Starlink. There we have the challenge that Starlink is sending its signals on a 250 megahertz wide channel. And that's way too wide for our HEC-RF1s. And I think there is no good available SDR that is capable of receiving those 250 megahertz. However, interestingly, they are sending at, they have sub-channels, and they are only 234 kilohertz wide, and this is absolutely in range to receive. So this is something we're currently considering looking into that, if it's still worth recording that, or what our options are there. Okay, so you see this is some work in progress. We're currently improving the system. Yeah, here's some sources that we used for the presentation. And as I mentioned, as I promised, here is the slide again. Everything of our project is on GitHub. Yeah, feel free to use it. If you have ideas how to improve on the system, contact us. We're happy about every feedback that we can get. Yeah, are there any questions so far?
Please, 2 questions. We're a bit time constrained because we had a slight miscommunication with the length of the presentations, but please.
Hey, thanks for this talk. Really wonderful. So I'll keep it to only one question, and I had several, but offline I'll do it. Ask you. So was there any privacy concerns? Because when you're recording Iridium data, right?
Exactly.
I assume there are subscribers who are making text messaging and phone calls. So how do you deal with that?
That's the reason why we decided not to share any of the data that we recorded. We have, as I just mentioned, 3,400 hours of recording. So 3,400 hours of communication of people that are not aware of that we are recording that. In the beginning, we considered sharing this, also opening up our network that we currently have. However, due to the privacy concerns, we decided not to do that. So yeah, it's an open point, and depending on the system that you're recording, something like privacy is they never heard of. Wow. So it's very PhD friendly, I would say.
All right, thank you.
So there are clearly difference between countries, right? Where you collected, please.
Okay, thanks a lot. It was a great talk. So I may be from the beginning, but are you what bands, frequency bands are you monitoring? So are you targeting for specific network?
Currently, we're mainly working on Iridium.
Oh, I see.
But
what bands are they? Which bands are they?
1.6 gigahertz.
So S bands, X bands, you don't know?
I think it's S band.
Okay, I see. So maybe it is related to privacy, but there has been a well-established kind of network for ground station crowdsourcing, like a SendNox. Why did you maintain your network separate from that?
Because it turned out that SendNox had a lot of already useful stuff for that, but also a lot of stuff that was it lacking of. So we considered that, but since we targeted directly LEO satellites, we wanted to implement the decoding functionalities and recording functionalities and so on, targeting to our LEO satellite group that we're working on. And as far as I know, that is pretty open to much more radio communication that's out there.
Thank you.
All right. Thank you. Let's thank the speaker again. And our second speaker. So yeah, our second speaker is Remy from the University of Colorado Springs, and yeah, we're moving from data collection and data analysis to satellite testbeds. So please, Jose, take it away.
Lovely. So thank you very much. My name is Jose. I'll be presenting today Space Cybersecurity Testbed, a Fidelity framework, an implementation and characterization. So a little bit about me. I'm a PhD student for UCCS. I have done this work jointly with my PhD fellows, Ekzhin and Caleb Chang, and my advisor, Shouhuai. So ideally, today I want to speak about a little bit about why we find that the cybersecurity is understood, and what motivates us to propose this framework, and then the characterization which leads to a testbed implementation. So the big idea here is that we have been studying cybersecurity incidents that happen in real world against space incidents, against space systems, sorry, and we found that mainly those incidents we cannot find proper descriptions about these incidents. So cybersecurity is not well understood in this sense. Mainly those come from newspaper reports. So this issue this impacts the research for cybersecurity. So in this sense, we are also interested in testing space cybersecurity in real systems. But the idea is that testing can lead to your system to crash. So testing in orbit is pretty complicated, and we have not found any collaborators yet that would let us test our results. So ideally, our contribution is that we build a framework of attributes where we can characterize testbeds, and then based on this framework, we will build. We propose a testbed implementation. So a little bit of the related work. Ideally, we found other 3 papers that speak about testbeds, and these are some of our benefits compared to these papers. I think our biggest one is that we're using realistic radio frequency signals. This is something that I have not found out there. Like nobody, I don't know why, nobody's doing realistic radio frequency communications. So this is a big headache for us. It took us a lot of time to make them work. So at some point, I understand why other people might not have done works with realistic link segment yet. So this is our testbed. Super simple testbed where we have our base is based on AMSAT satellite, just super simple AMSAT satellite. We have studied AMSAT, and based on that, we have developed on top of the hardware on AMSAT. So a little bit about our framework. Essentially, our framework is based on 3 types of attributes. The first type is system model attributes, where we present 4 attributes to characterize testbeds. So ideally, every testbed that we studied, we can inject into this framework and then compare other testbeds. So here, my most important takeaway in this slide is that our hardware fidelity is essentially based on 4 levels of abstraction. This is very important to us because when I went and compared testbeds, I had the issue that I didn't have the same level of comparison. So when I speak about a component, other testbeds might be speaking about elements, and other testbeds might be speaking about segments. So this is a way for us to understand what level do testbeds present results in. So since we use the framework to design our testbed, ideally we based the first attribute that we need to define is the mission. This is one of the most important attributes here, and then based on the mission, we define the rest. So essentially, hardware, firmware, software, and data collection goes after the mission. So a little bit about threat attributes. We have 2 threat attributes that we are essentially using to understand the attacks against the attacks that a testbed can accommodate. So the idea here is that in the ideal world, as we have studied real-world attacks and attacks proposed in the literature, we would like to understand if a testbed can accommodate both types of attacks. So the first attribute essentially presents a characterization for attacks, super basic. We base our characterization on 4 concepts: attack point, attack vector, vulnerability, and attack consequence. And then the idea is that we can use our the mission to understand how does the attack impact the mission. Yeah. So in this sense, for instance, we use the term functions to describe missions. I will jump into that later. So finally, we have the defense attributes. It's only 1 attribute, and essentially it just describes the defenses that can be accommodated by a testbed. So ideally, defenses can be employed at any of the element modules or components including communication channels that we have that the testbed accommodates. And testbeds generally can be described under traditional IT security controls, which we have found are common in the ground segment and deployed in ground segment solutions. And then we have a space infrastructure security controls, which essentially we have found are more for the space segment. So this is our system model. Essentially, this image describes the 4 levels of abstraction. We have segments. We incorporate 4 segments. Every segment is composed into components, and every component is divided into modules. And inside every module, we have the elements. So elements is the lowest level of abstraction for us. It's, let's say, is the real hardware that realizes the implementation, our testbed. Yeah. So in this case, you guys can see that we have in total for SDR elements, essentially HackerF software-defined radios, and we make them speak together. So the idea here is that now that we have a system model, which is our base, this is the skeleton. Without this, we wouldn't be able to produce any of the research. The idea is that we can categorize every single element and then understand the threat and the defenses that any element can implement. Yeah. So the first idea here is that we have a few firmware elements that run tailored firmware that we have built specific for those elements, and they just receive simple commands from. So the control, the first firmware element receives a command from the Pi5, which essentially is our brain and is the interface with the SDR. So the ground station, when the ground station sends a command to the satellite, the guy or the element that executes the command is the control MCU. We have a serializer MCU, which essentially compiles the data that's generated in the satellite and then makes one line of text with all the data and sends it to the Pi5. There are other firmware that we have not developed ourselves, that we use the firmware from the vendor. And at this point, at some point in the future, we will need to jump into study this firmware specifically. We didn't have time yet. So a little bit on the software. Essentially, we're running core flight system. This is a very common skeleton for a lot of satellites. And the idea here is that we have tailored a few applications to specifically for core flight system to be able to run in our testbed. Yeah. So our missions essentially are we can realize our missions. They exist thanks to these 6 applications. Additionally, our workstation is running Cosmos plus GNU Radio, and the user segment is just a simple messaging software that is connected to GNU Radio. So the idea here is that 2 users can communicate with each other remotely using the satellite. So our first and pretty big observation is that core flight system is prone to cyber attacks. So I think we all know this essentially in this room, but the idea is that where we will developing core flight system, the applications, we found that we found a lot of segmentation faults. And ideally, segmentation faults for us, we come from a very cybersecurity background, so I had to jump into space 3 years ago. So all my big background is on cyber. So segmentation faults essentially for me means DOS, the first and easiest thing to exploit. But then a segmentation fault, we can go for vulnerability or memory vulnerability related vulnerabilities. Yeah. So my idea here is that somehow we need to study these segmentation faults to be able to exploit them and then win control of the satellite. So a little bit on the data that we collect. These are some examples of the data that these are some examples on the data that we can collect. Essentially, this is the data. We call hardware-generated data to the telemetry that the satellite can generate. We call mission-generated data to the data that is essentially the payload, the data that the payload can collect. So in our case, we can collect images and we can collect communication messages. So a little bit about our missions. The idea here is that we have 3 missions in total. One mission we call infrastructure level mission, which is essentially the bus management. So how can the ground station manage the bus? And the second one is the application level missions. So this first mission is composed of two functions. The first function describes how the ground station can send a command to the satellite to control the satellite. Yeah. So the idea here is that the ground station can produce a command that will go through the SDRs, and then the Pi 5 receives the command. The control MCU is able to understand the command and then produces a signal for the solenoid valve, which is just super simple propulsion, or a motor which is connected to the solar panel, so it makes the solar panel and the satellite rotate a little bit. The second function essentially describes how telemetry is being generated. So essentially, these are all the sensors that generate data, telemetry data, and then, as I explained, telemetry data is serialized, and then the Pi 5 is able to pack that telemetry data. So we have two application level missions, which are essentially what the payload is going to execute. So the first one is our remote sensing mission. The ground station can send a command and then send the picture back down. And our second one is the communications missions. Essentially, two remote users can communicate with each other. The message will go through the satellite directly. Yeah. So our second observation is that, well, essentially the SDRs and the Pi 5 are, for us, is one of the key, are two of the key elements to understand in our architecture. So I'll jump into the threat model attributes. Essentially, as I have said, the idea is that we can test, we can test essentially attacks that happen in real world and attacks that have been proposed in the literature. In this case, we have selected an incident that we have studied a little bit deeper. In 2008, NASA's Terra satellite suffered two communications interferences, and other sources said that an attacker could have seized control of the satellite. Yeah. So our idea is that there's a ground station that's able to ping and get information back from that satellite. So our idea is that the attacker might have used that ground station. Yeah. So we have two threads that we can read from this incident. Yeah. For the sake of time, I will only be speaking about the first thread and how we can test this thread in our testbed. But these two threads can be drawn from the incident. So the first thread, our idea to evaluate attribute 6 is that we can understand this thread through the missions, through the functions in the missions. So in this case, we use the first function to understand the first thread. So the idea is that the attacker somehow needs to get access to the workstation. Yeah. So we can simulate that access using phishing techniques or any kind of physical access to that workstation. Yeah. After that, the attacker essentially discovers a buffer overflow vulnerability in the Pi 5 element. These are some of the vulnerabilities that we aim to find while understanding those segmentation faults. Yeah, this is the key idea behind the testing. Yeah, so the attacker can upload a malicious command with exploit code into the workstation. Essentially, the command is going to go through from SDR to SDR, and then ideally, the attacker will be able to reach the Pi 5 and execute the exploit code in the Pi 5. Yeah. So in this sense, from this thread, we understand that the attacker at some point needs to control the control MCU. Yeah. So in this sense, we're transforming this super simple description of an attack into the realistic way for the attacker to do this. Yeah. So after that, we speak about defenses. Ideally, defenses in general, as I said before, traditional countermeasures we find in the ground segment, more specific countermeasures we find for the space segment. So in this case, for instance, how could we protect against the attacker? So now we know the chain that the attacker is going to follow. So the first idea is that we can produce some phishing mitigation and firewall filtering for the workstation. Super simple, super common. Everyone is doing this. Yeah. So. But then we can propose more specific defenses. So in this case, for instance, we propose a super simple IDS that's based on behavior, and we can run it on the satellite. So the idea is that the satellite, this IDS, is able to interpret the command before the control MCU is going to execute the command. Yeah. So if the outcome is if the interpretation of the command, the outcome is going to be malicious, then the IDS prevents that command from being sent to the control MCU. So we never execute a malicious command. So how do we detect malicious commands? In this case, super simple. If one of the commands that's going to rotate the solar panel away from the sun, essentially, it depends on the amount of degrees, for instance, that's going to rotate. But if it's too big, we can just kill that command, because essentially that command will prevent the satellite from obtaining more energy or from recharging the batteries. Yeah, super simplistic. We haven't had too much time to jump into defenses. We're still understanding threats. So our third observation essentially is just that the fact that we can use the attribute 6 and understand the missions is very important for us, because again, some of the testbeds that I presented in the beginning are we haven't found either realistic missions or not even a mission. Like some people is just putting hardware together and call it a day. Yeah. So we need the mission behind. A little bit of our future research directions. Essentially, we want to go. We can go 2 routes. The idea is that we can produce more attributes to be able to incorporate more testbeds, and better testbeds that come up in the future will be able to use the framework to compare with other testbeds. So the idea is, for instance, that we produce an attribute that lets us describe a constellation, and we produce better attribute quantification. So the other way, which is something that we are really focusing on right now, is that we want to enhance the testbed. We have one satellite fully functioning and one is partially functioning. So we are trying to incorporate this new partially fully functioning satellite into the previous one. The idea is that we can develop and build more satellites so we can simulate a real constellation with inter-satellite links. And then other stuff that we want to put in there, which is super interesting. For instance, we don't have a battery management element or a battery management subsystem. This is pretty interesting for us because at some point, we would like to understand the cybersecurity implications of this. So imagine an attacker is able to impact your battery management system in your satellite. So the idea is that he makes the battery management system think the battery is way lower. Yeah. So automatically the satellite is gonna power off subsystems to reserve energy, to keep energy. Yeah. So this is the biggest next idea that we want to incorporate. So after this, I think I'm done. So I'll be waiting for questions.
Thank you, Jose. Yeah, we have time for questions. Do you want to come up here?
Hey, thanks for your presentation. I really enjoyed it. So I'm trying to understand the attack you talked about where you affected the mission of the satellite. So, I mean, looks like there is not much security really that an attacker can send a message to the satellite where it acts on it, right? So there is no verification of where the message came from, or no screening of there is no security protocol basically between in that link where it receives commands.
Yeah. So the idea, here is that essentially when we spoke, so there's security out there.
Okay.
So ideally, workstations to prevent this attack in the first place, workstations might need to deploy defenses. Yeah. Mm-hmm. So in this case, for instance, we can train operators to prevent phishing attacks, or we can even put some authentication into the workstation to prevent someone from sending a command to the satellite. Yeah.
Yeah, so there are security procedures in place as of now then, because I'm learning more about the satellites. I work on 5G and I know about what we're trying to do with NTN with satellites bringing into the 5G system. So 5G has introduced a lot of security protocols where like you have to get mutual authentication, right? TLS, then you have to actually OAuth and stuff, so to be able to even communicate, right? Mm-hmm. So I'm just trying to understand. But I think sounds like you're saying there are some security procedures in place, but one may forget to implement them, right? And
so for sure, I cannot speak from the industry, from the space industry perspective, because in this country it's very difficult to access in space industry information and whether they have a ground station where they deployed authentication, I don't know. From the literature, it doesn't look like it. For instance, we have found several papers. Well, the tendency for past communications within the space segment looks like there is not even authentication in between radio frequency communications. Yeah. So this is the perspective that we obtained from literature, essentially.
Got it. Thank you very much.
Thank you.
For some of the ground station positions, I can recommend FCC documents, for example. They have a lot of information. Often. We definitely have time for another question. Sam?
Yeah, Sam and Giroux, MIT Lincoln Laboratory. So I was wondering if you've looked at the Sparta framework. I think there's a lot of good information to help refine like your threat models and some of your access mechanisms.
We collaborate with
future
Sparta.
Work. Okay.
We collaborate with Sparta. Sparta has published some of the Sparta recent contributions come from our lab.
Oh, okay.
Yeah, we have looked into Sparta. I haven't had too much time to work on the Sparta route, but I was trying to understand whether the related work behind Sparta leads us to understanding more incidents, finding more incidents. But so far, I think the list of incidents and the list of resources that we compile is comparable to Sparta's.
Yeah. I think sadly there's even less willingness to share incident data than there is a lot of other things.
Yeah, we're on that regards. We're also trying to collaborate with the SpaceSec, which is actually next door to our facilities. So we'll see if we can get some information from that route as well.
That would be exciting. I'd be really interested to see future work when you get that.
Yeah, definitely. Thank you. We'll try to get there. Thank you.
Any final questions? If not, then let's thank the speaker again. Yeah, our third and final speaker for this session is Roy Dan from Ben Gurion University, and he will also be speaking on satellite cybersecurity testbeds. So I'm really curious the approach they are taking and how they compare. So please go.
Great, thank you. Good morning, everyone. My name is Roy Dan. I'm a master's student at CBG in Ben Gurion University. Today I'm excited to present our work on AegisSat, a satellite cybersecurity testbed. The work that my colleague and I did here was to think about a way to create a testbed that will be both open source, try to add more realistic environments into it, and to make it a controlled testbed, in which way we can actually really see how the testing occurs and understand exactly when the cyber attacks occur. So in this presentation, I'll go over the motivation for creating the testbed. I will go over the architecture that we implemented and discuss about the implementation of the current implemented cyber attacks. I will do a short presentation of one of the simulation runs that we did in our system, and then I'll talk about discussing future expansions that we're currently working on. Our aim is, like I said before, is to create a realistic and open source environment that you can plug in a satellite or take the satellites that we're working on and study how the environment and everything else affects it. So, as you probably all are aware, in the past decade, pretty much, the number of nanosatellites has grown exponentially from a few dozens to several thousands. This can mainly be attributed to new space, if it's improvement in technology in smaller satellites, reduced launch costs, and the increased participation of private companies. Here are some examples of some private sector companies that work in nanosatellites. One of the most prominent uses is for Earth observation. There is plenty of uses from agricultural to monitoring fields and disaster responses. Another key factor is for communication, where they're mainly used to extend the region for wide areas, to support IoT sessions, and to enhance connectivity in general. Another interesting point is for scientific research. It can be used from space research to pharmaceutical research and many others. So as this number of satellites continue to increase, the number of threat actors that begin to take interest in them has grown throughout the years. This can be seen, as we see, in the number of attacks that are currently being even made publicly available for us. And as mentioned before, the space sector is pretty closed off and does not discuss too much about cyber incidents, so we can safely assume that there are more cyber attacks that have been attempted or actually been successful that the public is currently not aware of. The point is that these attacks are not just theoretical, they are critical, and they are actually affecting real-world infrastructure. So one of the main problems with nanosatellites is due to the constraints of the launch and space and everything, they lack a lot of resources, which they prevents from strong and robust defense mechanisms. And as well, in addition, the main focus when designing and building satellites is for functionality in mind, and cybersecurity is usually put as an afterthought. And with what I just discussed about the number of threats that are being increasing to the field, is leading us to an increased threats for the satellites. One of the points that we saw is that there is a lack of place to study and understand the effects of cyber attacks on satellites themselves, if it's from the subsystems itself or how they are implemented. And this is where AegisSat comes in, and our goal is to create a realistic environment for satellites for cybersecurity. Okay, so there have been some work on excellent works on the field for testbeds that focus on satellites. One of the most prominent one is the Mitra testbed, which, however, it mainly focuses on the output, the external attack vectors on the attack, and does not, and mostly takes into account the satellite as a black box. Another interesting and excellent one was presented actually last year here is the Merge Space testbed, which uses virtual satellite networks to study how cyber attacks affect networks from denial of service, malware infiltration, and data exfiltration. However, again, they don't have a physical satellite, and they don't focus on the effects of the attacks on specific satellites. So the main gaps that we saw from the publicly available data that we have is that there is most testbeds currently use virtual environments, which are excellent. They don't always study the effects of how the physical environment and how real satellites, which are like, when you have the actual satellite, there's always edge cases and there's always points that can lead to errors, as well as the environment itself, if it's the sun and the power generation and other vectors that have. In addition, we didn't find any data set that has any labeled or any data about cyber attacks on satellites. With these points, we understood that there is a need to implement something that can be open sourced and that will enable further research in the field. So to address this gap, we developed AegisSat, which is an open source testbed design for studying the effects of cyber attacks on satellites. AegisSat is built to simulate both external and internal attacks on satellites, meaning the external part is pretty obvious, but the internal is more what happens when the attacks are already in the system. What if there is an attacker that managed to infiltrate using a supply chain attack or other vectors to actually have some way to control the satellite? And in addition, we wanted to create this in mind that it will be open source, that other labs or research facilities could take our design and continue and develop it even further. So the main architecture is divided mainly through the software and the physical component. The software-based is mostly how we simulate, we load the TLE, we discuss, we insert the parameters for the commands and operations that the satellite will occur. And the physical part is the actual CubeSat and the environment that goes around it. Our goal is to generate with it data that is labeled and is organized that will assist in creating machine learning mechanisms for defense and a better understanding. So this is the main design of how the currently AegisSat is implemented. There is a simulation manager that it's in charge of the entire testbed. It controls and relays information to all other parts. There is an emulation environment that simulates the environment, which we'll discuss later. There's the satellite itself that has the operation and that communicates with the operation and the control, and the attack manager, which is the part that implements the attack vectors. And yeah. So this is design of how we implemented the actual computers and everything in the system. What is important to note here is that each part is a different computer. The simulation manager is a different computer from the attack and the ground segment and the emulation manager. And this leads that only the relevant data for the scenario it will have access to. That means, for example, that the simulation manager just informs the information about the current time, for example. It does not have any direct access to the satellite itself. So I'll go over each part now. The simulation manager is it's in charge of everything. It oversees that everything is synchronized, meaning that each part understands what is the time and what information it has access to. For example, using TLE, most systems, like both the attack and the ground station, will have access to the location. So that is information that we can relay onwards. Additionally, because everything is timed and synchronized, we can create the experiments in a controlled environment, meaning we can repeat experiments and just change every time to tinker something small and then understand the effects on them. The physical components that we implemented are the CubeSat, which is a CubeSat that has everything from an EPS, OBC, ADCS, TTNC, and a payload. And it communicates directly through a ground station, which is in order to mimic the same operation that happens, and an environment setup. Our current environment setup includes a magnetic field generator, a solar lightning emulator, and an Earth view simulation. Each one helps us better simulate the scenario that the satellite will actually be in. The magnetic field helps us understand how the information affects the ADCS component, and the solar lightning emulator helps us both mimic how the telemetry will affect the sun and the power generation of the satellite, as the satellite is being charged only by the solar lightning. In addition, we have an Earth view simulation. You can see this is the screen below. In this, we mainly used when we wanted to study, we are currently studying some attacks on the payload of sensors that are imaging. In this way, we can insert scenarios and understand how they affect the satellites. So the operation component of our AegisSat is really as any standard operation on a satellite. There is a ground station, it communicates, it relays information, and it downloads telemetry. And yeah, the attack manager this is where all the cyber attack points are implemented. The point is that when you're loading a testbed, we wanted to think about the different attack vectors that might occur. So in some cases, for example, we can study the effects of a rogue operator and understand what effects can a rogue operator have during the scenario. And then we wanted to see we wanted to limit the access points for him to have only the limited data that he will have in that scenario itself. So each scenario, when it's defined, the attack manager will get access only to that specific information. And that way, we can mimic it to simulate as real as possible. So some cyber attacks that we currently implemented, one is malware insertion, where a malware is already inserted into the satellite. This can be from deleting files to moving files around and causing increased CPU usage. There is data poisoning, which is corrupting data. from telemetry to the actual data itself on the satellite. In addition, we implemented command injection, which manipulates what happens when an attacker can actually insert attacks and affect critical moments of the satellite. There is jamming, so I think it's pretty yeah, and falsifying telemetry, which involves what happens when an attacker has control of the satellite and he wants to use the satellite to use for submission, and he wants to falsify the data so the ground station will not understand that it's been used. So again, as I mentioned before, the simulation, our goal is to make it that it can be repeatable. So every time you create a simulation, you load the TLE, you load the operation commands that you're planning for the scenario, you load the attacks, and then you can repeat and collect the data as it goes. So this is an example of a sped-up example of a simulation run that we have currently run. The goal is that we can see that you can have a live simulation to understand what is currently going on the satellite. You have telemetry of the EPS, for example, that is shown here. There is a mimics that, like pointers, you can see on the left, there is currently an attack going on that uses an increased EPS. And this way, we are looking at two vectors. In this case, we are both collecting data and we both have a real live simulation. So researchers can better understand what is currently going on in the runs themselves. So as I mentioned earlier, all our data set we're currently collecting is everything pretty much that we can, which is the telemetry data, the attack planning, and every log that we can. Our goal in mind with this is to create data that can be increased and used. We're currently saving everything in a MongoDB, and then it's pretty organized. So we are using it to create the models, especially anomaly detection models, that can later improve the defense mechanisms of our systems. One exam scenario that we implemented for the testbed already is to research about the falsified telemetry scenario, in which an attacker has access to the satellite, it can use it, and he mimics the telemetry so the ground station will not know that anything occurred. For this research, we created an out-of-band chip that monitors the electrical signal of the satellite. And we downloaded all the data on a different side channel. This way, we were able to continue to do the monitoring of it. And our results were from this initial testing. We were able to actually detect pretty much just from the electrical signal which subsystems were activated, and then by that understand which subsystems were falsifyingly activated with a pretty high success rate. So again, all our code and the actual design of the testbed will be everything available. Our goal in mind is really to improve the field and to build upon it, to extend it even further. And we will be publishing some of our data that we are collecting, so we can also assist in researchers in the field, especially cybersecurity researchers that don't have access to satellites or access to the data itself. As mentioned in previous talks, it's pretty hard to get any data in our field. So our goal in mind is to make something that is open source, that might have a chance to work in space, but is not actual satellites that we will compromise the data of. Our current expansion plans is to simulate multi-satellite networks. We're currently working on implemented multiple satellites and understand how, in a physical level, the attacks affect on them. We're working on integrating more attack vectors, especially AI-oriented attacks, and we want to see how the defense mechanism actually affect the satellite, if it's from their power consumption to their accuracy. And we're currently working on improving the UI of it. this is our plan for the UI, so this way it will be even more informative for a researcher to understand what is going on live with the satellite. If it's from its location, its EPS, its telemetry data, the commands that are being executed and at what time, and all other parameters that will be relevant for the current research. So in general, our goal with AegisSat is to create an environment which can be repeated for repeatable experiments. Our goal in mind is to make it open source and that it will improve collaboration in the field. So thank you very much, and I'm happy to take any questions.
Questions from the audience? Maybe just a quick one from my end. What was the rough effort for this? I mean, this is clearly not just your master thesis. So do you have any idea what how long, I don't know, person, month, years to build this?
To do it?
Yeah.
Oh, I'm actually the one who worked on it. It's like a side project. It's like my main research, one of my research projects of the side. It took us a year and a half, pretty much, to create it. Like our goal in mind was first to design. We planned the satellite that we wanted to use. We're currently using how is it called? Sorry, I forgot the actual satellite itself, but we're planning on purchasing another satellites. We planned the magnetic field and everything, which again, we will be making public available our design and everything. So any lab or research-oriented fields that want to use it, we are more than happy to share even more information if needed. And then we began testing, which was to validate everything is as close as possible to real space. Our goal in mind, again, is to make the satellite think it's in space. So one vector that is actually interesting that we're working on is there are a couple of Israeli high schools that are currently launching satellites that monitor radiations in the field. And we want to add this layer of information of the radiation in accordance to the location of the satellites. And again, to add more layers, we're open to more suggestions and more ideas of how we can make the Testbed even better.
Very nice, thank you.
Okay, thank you for your great talk, Chojun from Kyung University. So you used the CubeSat, maybe 1U size, and did you purchase the commercial one? Because I want to know the details, like for example, it uses TM and TC compliant for the CCDS protocols, or how whether it is encrypted, it supports any security measures, because you suppose some spoofing attacks scenario during your whole system design. So.
Could you repeat the question again?
Yeah. So could you provide the details for the CubeSat that you used, like what TM and TC protocols it supports, or?
Yeah, we will we'll provide all the technical data on our GitHub, including everything, but we're currently actually planning on updating the satellite. So this is currently a work in progress, but our goal in mind is especially the testbed itself. It's like the infrastructure around it. That was the mind of the testbed itself, because we had a problem where we wanted to make it repeatable, all the points of it, and it doesn't matter which satellite is actually in it. That's the point, because we're currently working in 1U, and one of the main challenges that we have is that there is a lot of power limits for 1U, and a lot of missions use at least 3U or 6U. I personally worked in the past in a company where I worked with 3U satellites pretty often, and one of the points is that we have a lot of different power limitations with it. So our idea in mind was to say, okay, let's create this infrastructure that you can take this. The 1U, it doesn't really matter. Let's switch it to a 3U or a 4U in accordance to your need and for your research point of view. So that's how we were looking at it. But yeah, we will share all the information that we have from the TTNC and which EPS we're using and everything.
Thank you. And how would you estimated cost for building I don't know, buying 1U CubeSat and setting up this testbed?
It depends on your vendor for the 1U, actually. That's I think one of the challenges that we had as well. But I believe in total around $5,000, $6,000 is how much we worked on it. We had a lot of work time as well, and we have a lot of great electrical engineers that did the works and the methods for us to save some cash and all. But I believe that's around the estimation that we have. But again, we were looking to make it as quick, as efficient as possible, and we didn't think about monetary usage. The main point was the magnetic field that took a lot of time to spin it around to create it. That's the point, but the other stuff, the lamp and the earth view and everything were pretty cheap.
Thank you.
There's no final questions, then, oh, there's one. So we have a minute.
Hey, thanks so much. My name is Chris Ellis. I'm from Ohio State University. Excuse me, I'm supposed to introduce myself as a NDSS Internet Society Fellow. Thanks again. I just had a quick question about the out-of-band component. What method of signal capture and analysis were you doing?
So actually, this is one of my research of my colleagues, so I don't want to spoil too much of it. But we were using an out-of-band to just monitor and see. So for this scenario that I presented, we were physically using another antenna that we inserted into the satellite. So, but there is he has very interesting results, and I believe it will be presented and published very near in the future.
Okay, sounds good. Thank you.
And let's thank Roy and all our speakers for this session. We will